No. So this is my second video on building blocks of a finite element code, which is a course of advanced numerical analysis supervised by Professor C. Joachim. So this video will be in this video I will discuss about mathematical viewpoint of the code to implement into the finite element analysis and implement a code to make some nodes for a certain object, and discuss how to solve and what are the steps and the flowcharts and the flow of the work for getting a result in the finite element analysis. So yeah, we will realize the code implementation, explain general phenomenon and blocks of FEA. So from that paper I have found that this type of a shape function in a equidistance and with a equidistance equispaced nodes in the domain. So in the end of the video I will try to make this type of shape with the code. So this video's this video's description is referred from the Professor Bengert lecture 4. Actually this is interpretation. So from this video we will learn how to consider a strong form equations to a weak form equation for solving the problem, and basic step of the finite element analysis, basic cell formation, and the code to build the nodes for particular point. So you can see here this is the mapping of a certain object. This is how the mesh can be created. Well, for a mathematical viewpoint, here the Poisson's equation is referred here. So in this case the left hand side and the right hand side will be the same, and there are some arguments about that. If we can assume the f is equal to 1, then we will get the derivative 0 here, or sometimes it is said that we will not get a solution for all the situation or conditions. So it was assumed that before there would be no solution, but there should be some solution here, though it cannot satisfy all the criteria. But yeah, we can get the desired solution. Presume it's true, right? So after transforming into the weak form with the derivation of like that, actually this is the multiplication by the by a test function. So if we multiply with the test function, then we can get the weak formula. So there is a trick to solve this type of problem. We should have multiply the test function in the left side to avoid the difficulties. If we just multiply the test function in the right side, then there would emerge some type of inverse transpose of a matrix. So it will be very difficult. Sometimes it will be difficult to calculate. So however, this weak form of with the test function can give us the desired value, but but the problem is it will give an infinite number of solution. This function would provide infinite dimensional solution that can be very tedious for calculating or for computation. So for ease, we will transfer this type of formula or equations into the discrete form for a finite dimensional function of the form. And if we just this is the form from this finite dimensional function, where this is the this form is expressed as a linear independent function, where there are n equations with for the n coefficients. Okay, so this is basically called the Galerkian method. Well, here the nebula of phi I and nebula of u is equal to the phi and f, which must be equal. Actually, the left hand side must be equal to right hand side, but sometimes it turns out that it must be the same for particular function, for each particular function. Okay, so what are the steps, how the steps are done for making the shape function and ultimately to the final result. So the subdivision of the domain are turned into the mesh, and actually the mesh defines the each cell and defines the mapping for the reference cells. And if we can evaluate this mesh, we can get the shape function that define actually the degree of freedom of a global mesh. Also, if we can enumerate this area, then we can get the we can also get the area or other properties globally. And in my previous video I have demonstrated that how we can detect these points with the shape function, or by applying Gauss quadrature rule. Well, from the basis function, if a bulk object is like that, it can be turned into mesh, and this type of mesh can be obtained, and which is called the mapping. And this is the reference cell which is embedded here. This shape can be triangular, rectangular, hexagon, tetrahedron, depending on the corners, or depending on the shape of the bulk modulus. Bulk object. So for solving this type of equations, there would be various type of solvers like DX solvers, iterative solvers, or parallel solvers. Actually, these type of solvings are quite large in scale. There could be many types of solution here, the DX solvers, iterative or parallel solvers, because there are this is a large scale of computations for data structures or algorithms for data structures, and for that the algorithm must be parallel. Well, before we have stated the discrete function, which can be expanded in a bilinear form like this. So for obtaining the solution, we can get this type of form. So actually, if we turn this type of form in the linear system, then we can get A U is equal to F, where A is the sparse matrix. So how we can solve it? We can solve it in a two conceptual way. The two conceptions are here: mapping and quadrature. So first of all, for mapping, there the integration must be done for the value of k. K is the number of meshes here, and jk defines the reference. This is the Jacobian inverse matrix, and this term is for just a minute. This term is for the phi I, and this is for the phi j. So from that type of equation we can get the mapping. And for quadrature, which was explained in the previous videos, so the quadrature, we can get the same type of values here. If it needs double integration or double summation, then we can tell that this one, the value of Jacobian matrix and xq and weighting function, that can be works as dx for these functions. However, we will get to the next slide here. So where the A matrix would be stored, this would be stored in a compressed row format, and the U will be stored as an array, and like the left hand side solve, we can also solve the right hand side similarly, and we can get the f for the phi and f. Well, after the solving, what we can do the post-processing. This can be visualization, this can be visualization, or evaluate the quantities of the interest, or we can estimate the errors between two results if it's needed. So this is the flowchart, how this whole type of steps works together. You can see here the triangulation, finite element, quadrature, and mapping. So this defines the finite element, which is actually shows the reference cell of the finite element, and the quadrature, we can get the points and the values of the and the properties of the meshes, and mapping shows the reference cells. And what about the triangulation? Triangulation is the collection of cells. So together with these two terms, it defines the degree of freedom for the global mesh or global coordinates. And the quadrature and mapping term, and also the finite element, these three terms evaluate the finite element values that is needed for solving. So after defining the degree of freedom and all the important finite element values, we can get the discrete system. And if we can get the discrete system, something like that, so we can solve it, and after solving it, after post-processing, we can get the visualization or calculate the evaluation and errors. So this video is the concepts that need to be represented by the software components, how the software works step by step, and other components related to solve the PD or other types of equation, which is which has presumed to be have no solution, but it can be done step by step or in a discrete form, and we can transfer the discrete form in a bilinear or linear um, form, and we can calculate in various concepts like quadrature concepts or mapping concepts. And after solving that, following this flowchart, the software actually works like that. So now we will make a video we will make a video for actually coding based on the Python. So I will demonstrate the nodes how the nodes can be created in this plate with a crack like this. This is actually a parabolic shape, the crack. So we can control the mesh. We will do the meshing in the later video. So I will demonstrate how the nodes are created here and how the number of nodes can be controlled with the code. Okay, thank you. Now I will demonstrate the codes. So this is my virtual box deals to Linux setup. In this in a folder I have made a file here, just made a file like that. Create a file, maybe crack.py for Python program, and if you click it, if you write something here, then it will be considered as the Python code. So previously I have made the file. Well, actually these 3 lines are the three Python module: the import math, matplot, lib.pyplot, and the numpy and others. So we can write here as a comment that 3 Python modules. Okay, so if we want the nodes, say for example I need the nodes for on a rectangle. Just a moment. Is this recording? Okay, sorry for the interruption. Well, I will define a rectangle, not a rectangle, just define 4 points of a rectangle like that first of all. So if the axis is like that, x and y, if axis is like that, x and y, then I will define a point here which will be 0 0 1 0 1 1 and 0 1. So this is the basic. After that I will go for further steps. So let's consider about 0 comma 0 comma 1 comma 0 less 1 comma 1 and 0 comma 1. Okay, so this couldn't be printed like I want, so I will give an array dot np array. I'll make a bracket here is equal to okay. Now I will print the nodes plt plot. I'm sorry. Yeah. plt plot nodes like it will start from the 1 and sorry, it will start from the 0 and go to the nodes of 1. Okay, and I will put a O here, and there is a problem, so I will close it. Nodes, it will start from the 0 and it will run up until 1, and I need to show the plot. Show. Let's see it works or not. Just save it. Open a terminal here. Write Python 2 since it's in this directory, so I don't need to define the change directory here. So the file's name is coordinate.py. There is some bugs here. So the bug is here is a extra bracket, so I have removed it. You can see that. Then save it. Now run it. So here are 4 points. If we change the coordinate here, then how about this one? If I put it like 2 and it's 5, how about this? Yeah, you can see that 0 0. Okay, I have to give 10 maybe. So now I will not change the code here right now, so I will make a new code maybe to define the whole square. How about that? So if I copy it and paste it, and I'm going to rename it as a rectangle. Okay, so for this one I need to delete this one. I have to define the length. Length is maybe 1. Height is equal to 0.8, 0.8, and since I will make this type of plate with this type of crack, so I will make the r the radius. This is the parabolic, so let's get to that. R is equal to maybe r 0.01. Okay, so these are the parameters. Okay, now how about the node number, element number actually. So the element number would be element. Okay, I will give 30 elements here. So instead of defining discrete points of the node, I will define as for loop by applying the for loop. So I am applying the nodes like that, and for loop I will use for, then x in np. I will use the np line space, which will start from 0 and goes up to length L. And how about the number? Then the number would be element number. Yep. So what about the np line space? So this is the start. So np line linspace start, last, and the number of element. Okay, so since there are two axes, x and y, so we will make a nested loop here. For nested loop I will apply for, this is same, it will be y, and it will start from the 0 and goes up to h point. The number of elements will be like that, or you can modify this one, and I think it's okay. So now I will apply the append. Actually append will add all the elements to the end of the list. So in this case I will apply the node here. So since I have written node, so I will return node here. So node dot append x comma y. Yeah. Okay, and now this is done, I think. So for display, the points will be the n of elements. Wait a minute. Yeah. Point of the element, which no, actually the array of the node. So np array of the nodes. Okay, not node. So for the plots, we'll apply the plot. Yeah, in this case, since the node is in the array, so I will apply here the points here. So I think it's ready to go. Let's see. So if you run it here, for example, yeah, there's some bugs here for this line 16. So I think, yeah, there's a missing colon here maybe. So let's do it again. So I need to change the dimension here for fitting into the graph. Now it seems okay. Yeah, something like that. So the length is 0.1 and the height is 0.4 here. And the mesh number, we can change the mesh number, like if we change it 30, yeah, like that. So not mesh number, actually the elements number. So if we go for 50, or if we go for whatever 15, okay. So now I will make another one to make a crack, like that. Well, so I'm gonna close it now. Yeah, we'll rename this file. I have copied this file and rename this file crack. However, I have renamed this one poor because this is a file that has been created here. Yeah, we can edit the crack one, this one. We will copy the first one and save it. Let's see. Yeah, it's done. I will delete this one. Okay, so let's edit this one. So since this is something like this parabolic, so when it will starts from here, then the radius is r, So when it starts from here, then x is equal to 0, but y has a highest value, right? And when it comes here, when then x is the highest value and h is equal to 0. Okay, so we will make this statement for the if and else. Well, so let's insert it. Okay, so now if x is less than r, then y not will be square root r square plus parabolic x. Okay, like that. And for this one, it will start from not 0, it will start from y not. And I think it's done for if statement, and now for else statement. Yeah, here is a colon. For else statement, I will write for y. Yes, actually after this portion it will be same like the previous one. Okay, so I will copy that. This will start from the 0, and it will come later. I think it's done. Run that code here. I'm sorry. So here is the result. This is quite like the parabolic, and it starts from point, since it's 0, 1, so you can see here from here is 0.01, it's 0.01, and the height is 0.04 and the length is 0.1. And also we can control the element number. Yeah, so thank you. You will get the code in the GitHub repositories. Also, this is quite similar to and code from GitHub repositories. They have used the circular path here. So let's clone their let's clone their GitHub repositories. I have forked their repositories here. This is one of the famous YouTuber. I'm going to collect his repositories here. So now make a folder, git repositories, make terminal here, write git clone and paste. So now we'll run their file simply mesh. This is the change directory. We'll copy that directory, cd, paste the directory here. This is the yep, there's some problem maybe. Yeah, so change directory, type ls. There are two arguments, so I will open the terminal here, python 2 simple mesh .py. Here their crack is this is quite similar. The crack is circular, and depending on that code I have built my Python code here. So you can get my code in my GitHub repositories. Thank you.